Multicore architecture by Yordan Krustov and Ivalo Ivanov. A transistor is a semiconductor device used to amplify and switch electronic signals and electrical power. It is composed of a semiconductor material with at least 3 terminals for connection to an external circuit. A voltage or current applied to one pair of the transistor's terminals changes the current through another pair of terminals. Because the controlled or output power can be higher than the controlling or input power, a transistor can amplify a signal. Today, some transistors are packaged individually, but many more are found embedded in integrated circuits. The transistor is the fundamental building block of modern electronic devices and is ubiquitous in modern electronic systems. A central processing unit, or CPU, is the hardware within a computer that carries out the instructions of a computer program by performing the basic arithmetical, logical, and input/output operations of the system. The term has been in use in the computer industry at least since the early 1960s. The form, design, and implementation of CPUs have changed over the course of their history, but their fundamental operation remains much the same. A computer can have more than one CPU. This is called multiprocessing. All modern CPUs are microprocessors, meaning contained on a single chip. Some integrated circuits, or ICs, can contain multiple CPUs on a single chip. Those ICs are called multi-core processors. 2 typical components of a CPU are the arithmetic logic unit, ALU, which performs arithmetic and logical operations, and the control unit, CU, which extracts instructions from memory and decodes and executes them, calling on the ALU when necessary. The transistor count of a device is the number of transistors in the device. Transistor count is the most common measure of integrated circuit complexity. On most modern microprocessors, the majority of transistors are contained in caches. As of 2012, the highest transistor count in a commercially available CPU is over 2.5 billion transistors in Intel's 10-core Xeon Westme Rex. According to Moore's law, the transistor count of the integrated circuits doubles every 2 years. The law is named after Intel co-founder Gordon E. Moore, who described the trend in his 1965 paper. His prediction has proven to be accurate, in part because the law is now used in the semiconductor industry to guide long-term planning and to set targets for research and development. The period is often quoted as 18 months because of Intel executive David House, who predicted that chip performance would double every 18 months, being a combination of the effect of more transistors and their being faster. Although this trend has continued for more than half a century, Moore's law should be considered an observation or conjecture, and not a physical or natural law. Processors were originally developed with only one core. Multi-core processors were developed in the early 2000s by Intel, AMD, and others. Multi-core processors may have 2 cores, dual-core, e.g. AMD Phenom 2X2, Intel Core Duo, 4 cores, quad-core, e.g. AMD Phenom 2X4, Intel's quad-core processors, 6 cores, e.g. AMD Phenom 2X6, Intel Core i7 Extreme Edition 980X, 8 cores, e.g. Intel Xeon E7-2820, AMD FX 8350, 10 cores, e.g. Intel Xeon E7-2850, or more. A multi-core processor implements multiprocessing in a single physical package. Designers may couple cores in a multi-core device tightly or loosely. For example, cores may or may not share caches, and they may implement message passing or shared memory intercore communication methods. Common network topologies to interconnect cores include bus, ring, two-dimensional mesh, and crossbar. Homogeneous multi-core systems include only identical cores. Heterogeneous multi-core systems have cores that are not identical. Cores in multi-core systems may implement architectures such as superscalar, VLIW, vector processing, SIMD, or multithreading. Multi-core processing has interrupted the ongoing race among chip designers to create ever faster processors. By using multiple slower cores, it is possible to achieve higher clock speeds more efficiently than by designing super-fast individual processors. When personal computers using multi-core processing technology first became widely available to consumers, in 2003 and 2004, the new CPUs featured only dual-core processors. This quickly changed in subsequent years, with multi-core processing becoming the standard. Quad-core and octo-core processors will allow for chips containing literally hundreds of cores or more. Multi-core processing is not limited to the realm of personal computers. Many other electronic devices, including game consoles, industrial electronics, supercomputers, as well as PC hardware components, such as the graphics processors on video cards, use this technology. The improvement in performance gained by the use of a multi-core processor depends very much on the software algorithms used and their implementation. In particular, possible gains are limited by the fraction of the software that can be run in parallel simultaneously on multiple cores. This effect is described by Amdahl's law. In the best case, so-called embarrassingly parallel problems may realize speed-up factors near the number of cores, or even more if the problem is split up enough to fit within each core's cache, avoiding use of much slower main system memory. Most applications, however, are not accelerated so much unless programmers invest a prohibitive amount of effort in refactoring the whole problem. The parallelization of software is a significant ongoing topic of research. Here we can see a list of Intel's processor range and the years that they came out, from 1993 to 2011. We start with the Pentium family, which was commonly used until 2007. This year was crucial because of the newly developed technologies such as dual-core and Core 2 Duo. Nowadays this multi-core technology is at its finest days. Hyper-threading is a technology developed by Intel Corporation. It is used in certain Pentium 4 processors and all Intel Xeon processors. Hyper-threading technology, commonly referred to as HT technology, enables the processor to execute two threads, or sets of instructions, at the same time. Since hyper-threading allows two streams to be executed in parallel, it is almost like having two separate processors working together. While hyper-threading can improve processing performance, software must support multiple processors to take advantage of the technology. Fortunately, recent versions of both Windows and Linux support multiple processors, and therefore benefit from hyper-threading. For example, a video playing in Windows Media Player should not be slowed down by a web page loading in Internet Explorer. Hyper-threading allows the two programs to be processed as separate threads at the same time. However, individual programs can only take advantage of Intel's HT technology if they have been programmed to support multiple processors. The first-generation Cell Broadband Engine (B) processor is a multi-core chip comprised of a 64-bit power architecture processor core and 8 synergistic processor cores capable of massive floating-point processing, optimized for compute-intensive workloads and broadband-rich media applications. A high-speed memory controller and high-bandwidth bus interface are also integrated on-chip. The breakthrough multi-core architecture and ultra-high-speed communications capabilities deliver vastly improved real-time response, in many cases 10 times the performance of the latest PC processors. The Cell B architecture is OS-neutral and supports multiple operating systems simultaneously. Applications may range from a next generation of game systems with dramatically enhanced realism to systems that form the hub for digital media and streaming content in the home, to systems used to develop and distribute digital content, to systems to accelerate visualization and supercomputing applications. Now the laws of physics are threatening to destroy the windfall. Simply put, transistors have to be made from atoms. As you shrink transistors in order to pack more of them onto a chip, you eventually reach a point where you run out of atoms. Even before you run out of atoms, the reliability of the smallest transistors decreases, and the cost increases due to the increased complexity and difficulty of producing them. Although recent innovations, like Intel's 3D transistors, have allowed us to pack transistors even tighter, the focus is beginning to move away from this density-driven approach. Moore's law of transistor density may be dying, but if we can be clever at other stuff, it can still live on in its broader definition of exponential growth in computing power. Parallelization, making chips that work more like our brains, is one way of being clever. Modern chips already have lots of slack that we can't exploit effectively. By imitating the brain's ability to distribute tasks, we can get more out of what we already have. For that reason, some people have set their sights on achieving the near impossible, replicating the human brain. Called Spinnaker, the project is a huge experiment in parallel computing that aims to use 1 million ARM processors to recreate the complex and networked machinery of the brain. And just as the brain's neurons are not the sharpest tools in the box, the Spinnaker project uses processors that are far from the cutting edge of chip technology. The progress in architecture has to some degree been a bit lazy, because you've always been able to get progress through Moore's Law. Now that Moore's Law is delivering less, it's time for the architects and software engineers to start delivering more. Running programs in a fluid, parallel manner across combinations of high-power and low-power chips, like the latest generation of ARM processors does, has the potential to sustain Moore's Law beyond the fundamental limits of miniaturizing transistors. Others are placing their faith in quantum computing. The appeal of a quantum computer is that it transcends the current paradigm of 0 and 1s, allowing a bit to be in a potentially infinite number of states, and so opening up the possibility of doing many computations simultaneously. Of course, the technical challenges are just as significant. Quantum states change once you interact with them, so it's very hard if you start doing things with a quantum state, like computations, to keep it nice and well-behaved. For that reason, creative approaches to parallel computing, as well as more experimental research into alternate materials and quantum computing, are not only desirable, they're necessary. Moore's Law must live on, and in more ways than one. The human brain is the key.